Welcome to 5-Minute Papers on AI for the Planet. I'm Grace Lindsay. Our paper today is Learning Skillful Medium-Range Global Weather Forecasting. Let's get started. From governments needing to put out evacuation alerts to anyone trying to plan a picnic, accurate weather forecasts make our lives safer and easier. For decades, to create forecasts, scientists have relied on numerical weather prediction models. These are systems of equations based on our understanding of the physics of the ocean, atmosphere, and land that are run on large supercomputers. The success of these models is an impressive feat of science and ingenuity, but making them better is hard. It requires scientists to analyze data, look for trends, and decide how to compactly capture those trends in their equations. Like in so many other domains, it seems like weather forecasting could be improved by building models that learn directly from the weather data itself. And that's just what this paper does. Specifically, it uses graph neural networks. Graph neural networks are a type of artificial neural network that takes in graph data. Graph data is any data that can be represented as a network of nodes and edges. In a social network, for example, the nodes would be people and edges would be connections between them. For modeling the Earth, nodes can be locations and edges can be interactions between those locations. What the graph neural network does with this graph data is called message passing. In message passing, the value of each node gets updated based on information from all of the nodes that it is connected to. How exactly to do this updating is learned by training the model to perform a specific task. Here, the task was to take in recent weather variables and predict what their values will be 6 hours into the future. Let's look at this model, which the authors call GraphCast, in more detail. The weather variables the model takes in includes things like temperature, wind, and humidity. Such values are defined for multiple different levels of the atmosphere, from the surface through the stratosphere. To represent the entire Earth, the globe is divided into a grid, where each point on the grid represents a square of up to 28 by 28 kilometers. Altogether, the current state of the weather is represented as one vector of multiple climate variables for each of the over 1 million locations on the Earth's grid. This information for the current state plus the state 6 hours prior then gets passed into the graph neural network. The main part of the neural network used for prediction is called the processor, and it performs multiple stages of message passing on this weather data. What is particularly clever about the structure of the processor is that it allows for interactions on many different spatial scales. The weather system is complex. Atmospheric dynamics at one place can quickly propagate and influence weather at another. To make it possible for the model to capture these dependencies, every node in the graph has edges that connect it to nodes at multiple different distances away. After several layers of message passing on this kind of architecture, the model is ready to make its predictions. Through a decoder, the activity of the processor is projected back onto the grid representing the Earth. The values at each grid point in the output represent how those weather variables should be updated. So by adding those updates back to the original values, you get your predictions for 6 hours into the future. Now, of course, we want to be able to predict the weather days or even weeks in advance. For longer-term predictions, the authors run the model on autoregressive mode, meaning that the model's own predictions are fed back into it to create predictions at another 6 hours and another 6 hours, all the way out to 10 days into the future. The longer the model is run for, however, the more computational resources it needs and the more difficult it can be to train. So the authors spent most of the training getting the model to do just one 6-hour ahead prediction. They then refined the model to make it work better on longer timescales. Even with this trick, the model took 4 weeks to train using 32 parallel TPUs. But once it's trained, the model is fast. It can produce a 10-day weather forecast in under 60 seconds. A comparable traditional weather model might take about an hour for that. And its predictions are good. There are certain locations and weather variables that it struggles with, represented here in red, but for many variables, it performs the same or better than numerical weather prediction, especially at longer lead times. It can also capture extreme events like cyclones and heat waves. From a practical perspective, accurate predictions of these anomalous events can be extremely important. Another benefit of the model is that it can be continually updated to enhance its performance. In fact, the authors show that when they train the model on data from 1979 up to 2020, it performs better than when restricting training data until just 2017. Climate change is going to continue to push our weather systems into new and different states of behavior, and that makes it even more important that we have these kinds of trainable forecasting models that can adapt. The authors are careful to note, though, that machine learning-based weather prediction isn't meant to completely displace traditional numerical models, which have features and abilities not yet explored in these trained models. But they do hope that their work makes clear that these methods are mature enough to contribute to accurate forecasting. That's all for this episode. Make sure to subscribe to this channel for more examples of how AI and machine learning can help protect and predict our planet.